All right, recording is rolling. It is Tuesday, April 23rd. So we're going to pick up about where we left off yesterday with this statistics packet, right? So in this packet, I got puzzle A, B, and C, right? We finished most of A last week. I'm also going to give you guys a recap because I know it was like 4 days ago. You guys come back from a 3-day weekend. Most of you guys back on Friday was the first time you'd seen any of these concepts as statistics. So I'll do a review with you guys, right? And then we'll pick up and finish the rest of this, and we'll do part B, which involves a lab and meter sticks, and you guys get to measure each other's heights. So you know that. Right? All right, so what we're trying to figure out um, back on Friday was how do we make sense of statistical probabilistic data, right? Which is really a bridge to the last main topic in this class, which is going to be quantum mechanics. Because I think if you have an understanding of statistics, then quantum makes a lot more sense, right? Okay. The final exam, everything's in January, right? Yeah. So yeah, I'll do a review with you guys, right? So yeah, be a thorough review just like the last semester too. Yeah. So if I asked a question like how long is this G2 gel pen? You're like, okay, well, that'd be really easy, right? You just take out a ruler, measure it, bam, there's some definitive answer, right? If I say, how long is any G2 gel pen? Well, it's, they're all probably kind of manufactured the same, so they'll something like, right? And in this class physics, right, there have been pretty well definitive answers all along, right? Like, what's the mass of this object? How fast is it moving? Where is it located? Right? All those are, there's some definitive answer, right? But when we get to quantum, a lot of answers you can only express probabilistically, right? So if you understand about probabilities, it helps, right? So we're looking at different populations, heights of things, right? Heights of dogs, heights of people, heights of trees, right? So we could kind of compare, contrast different groups and what can that mean, right? And these two main metrics of like a mean average and standard deviation. Now, mean average, you guys have probably been doing since elementary school, and probably a lot of times in this class too, right? So you add up all the values, divide by the number in the set, and that gives you like kind of a middle-ish type value, like a mean average, right? Uh, but what about like how spread out is some data? So we were putting together these bell curves last week. Here, I got kind of an example here, right? From where could this come from? Well, it could start off like a bar chart. It said like what is the height of something in some population, right? And you start counting numbers. And suppose you get like thousands of data points, right? So you got these incremental bar values, right? Right. When we step back and look at it, right? What'll usually eventually develop is some kind of bell curve, right? Now we're gonna make an assumption this is called what's normally distributed, right? So normal distribution, not all data is, but we're assuming it is, right? Okay. And then if everything was like pretty much the same height and there was no variability, like if I measured a bunch of these type gel pens, I bet they all come out to the same length, maybe plus or minus a millimeter, maybe, right? Okay. So there'd be like a real tall standard curve for like everything would be pretty much one bar. Right? But if you said like heights of trees or heights of dogs or heights of people, well, now there's going to be some variability. And how much variability are we talking about? Because dogs, remember, they're like hugely variable. You get little chihuahuas, you get Great Danes, you get medium-sized dogs, but all people. I mean, people are kind of about 5 or 6 feet tall, plus minus a couple inches. We're all kind of the same height-ish, sort of, right? Right. Every once in a while, you get like a basketball player or Tyrion Lannister, but besides them, everyone's kind of falls within. Right? So, how do you measure how variable? And standard deviation could be on a bell curve, the distance from the mean, right, which is this peak right here, to this inflection point. Now, you guys remember inflection point is where it changes from being concave down the middle to concave up on the tails, right? So that distance right there, hey, that could be a way to how spread out is the data, right? So if it was like a real narrow curve, it'd be a smaller standard deviation. If it was really spread out, that'd be a larger standard deviation. Right? And we were crunching the data and finding out what is the mean and the standard deviation for, again, these populations, dogs, people, and trees for their heights. Right? I gave you guys a process how to find standard deviation, and we did one of these out on paper. Right? And it took like a whole page of paper. Right? But then for the rest of them, we just threw the numbers in the calculator and did from there. Right? Now, ideally, out in the world, if you have a job one day where you do something like this, then you really ideally want hundreds of data points, not just 5, right? But we're making some simplifications. We're gonna take these 5 data points and say extrapolate some information about it, right? Okay, so you guys good so far? You guys remember that? Okay. And then right. So okay, so more I got to say on that, but we'll get to that later. Okay. There was a new concept we got right, kind of near the end of class back on Friday, which was this idea of z-score, right? Which is essentially a count of how many standard deviations from the mean is a particular individual, right? And it could be positive or negative, right? If it's positive, that's like above average. If it's negative, that's below average. And how you find it is you take the individual value, like say like your individual height. You guys are going to do this the end of class today, right? Subtract the average. Say, okay, so right there you can tell if you're above or below average. But then the next question, well, how much above or below average? Well, you get that by dividing by the standard deviation. So you're effectively getting a count of how many standard deviations above or below the mean are you. Okay? And then you can take that number, and we were looking a bit at, if you flip your packet over to the backside, there's the z table, which is in two halves, the below average half and the above average half. And I'll tell you for some particular z-score, which is on the left column, right? Again, it's the count of how many standard deviations from the mean, right? Tells you what percent of the data is filling up the curve up to that point, right? So like how much, okay, so like where do you stand within some entire population, right? So we're starting to answer those questions, and that's where the bell rang. Right, so let's pick up right there. I think we'd answer this question number 4 back on Friday. We've got a particular dog, individual height is, okay, no, again, my numbers are different than yours, but beyond that, we've got the end is here. That's it. So this particular individual, I'll show you guys the last one we got here. Right, so I'm saying z-score is your individual value minus the average, all divided by standard deviation, right? It's a count of how many standard deviations, right? And I'm saying I got a 60 centimeter dog, right? Subtract the average. Now the average had to go back to dog data, which is, okay, I got 93 centimeters is the average, right? Now right away, I see this is a short dog. This is probably a pretty short dog, but how crazy short? Well, it depends on what standard deviation is. I got 15.73, right? All these numbers are centimeters, centimeter, centimeter, centimeter. Right? So I did that minus that, all divided by that, right? That's gonna be basically that, right? So about 2 standard deviations below the mean is how short this dog is. So negative 2.1. Okay. Hey, you guys ready for the next question? Number 7, a dog with height 93 centimeters. So let's check out for that dog. Right, so I got 93 centimeters minus the mean, which also happens to be 93 centimeters on my paper. Be a different story for you guys, right? All right, well, then it doesn't matter what the standard deviation is. Crunch the numbers, 0, right? I'm going to get 0, right? If you have the mean value of something, in this case, height for dog, right? Then you have a z-score of 0. You're 0 standard deviations from the mean, right? Right? Everybody good? Right. Remind you guys how that aligns with this table on the back. Right? So let's look at the table on the back with us, right? So z-score of 0.00, right? And the cell says 0.5000, no, because that I can interpret as 50%. All right, so this bell curve would be shaded in up to 50%. This particular dog is taller than 50% of dogs, which also implies he's shorter than the other 50% of dogs. Right? This dog's right in the middle. Right? 0, 0. Okay. All right, you guys good? All right, let's go to next question. Human height of so many centimeters. Okay. So z-score. I got this many centimeters tall human. Okay. Subtract the mean. Oh, okay. Well, this mean is also the same. So okay. Okay. Divide by standard deviation. Okay. I'm getting again a z-score of 0 for this particular person. Okay. All right. You guys getting a z-score for number 5? Okay. I'm getting donuts. Move on to number 8. 5. Let's do number 8. Okay, z-score for let's say like a tall person here. Ooh, 200 centimeters. All right, here's a pretty tall person. But how tall? How can I quantify that? Well, that's what all this is for. Right, so subtract the mean. I can say how many centimeters above average is this guy. Right? Okay. And then that's in parentheses, then divide by. Got this many centimeter standard deviation. Right? Standard deviation thing, but sort of like a plus or minus value, tell you how wide that curve is. That's it. Put it all together. So that minus that in parentheses divided by that. Okay. Ooh, that is a pretty big z-score. 2.45. That is pretty up there. Right, 2.45. Okay, well, that's pretty close. Bam. Right. So you guys got a number 8. You guys got a z-score on number 8, right? Right. Now, before we move on, let me show you guys the context of what that means. Let's flip over to the z table. Here's 2.4, and then if I go over to the right, I can get one more digit of precision. 2.40, 2.41, 2.42, 2.43, 2.44, 2.45. Oh, wow. Okay, this cell says, let me zoom in on it where you guys, at least in class, can read this. 2.45 says 99.29%. It's at 99.29%. Okay, so what that means is this particular individual is taller than, let's call it 99% of other people. Right? So he's so tall that not even probably 1% of people are taller than him. Okay. Okay, guys good? Right, and number 6, tree. Right, so number 6, I got a tree of height. Is it 300 centimeters? Is that tree? 300 centimeters? Okay. All right, well, what's an average tree? All right, just go over here. Okay. So remember the trees I picked back on Fridays? Well, maybe this a good story for these trees could be, maybe this is a warehouse full of Christmas trees. And so these trees have been selected, or maybe the tops have been chopped off, so they're all sort of the same height-ish. I mean, not exactly as uniform as like manufacturing this pin, but there's not a lot of variability in these trees, right? Okay. So we got this warehouse full of Christmas trees. I pulled a random one out, this many centimeters tall. Here's my average, which we figured out back on Friday. Okay, so take the difference. Okay, now right away I see this tree is a little bit shorter than average, but not that much shorter than average, right? It's probably pretty close to average, right? But what does that mean? How close? Right? I'd like to quantify that. Well, that's what stats is for, and the z-score. So standard deviation is like this many centimeters. Again, think of this like a plus or minus type factor, right? Oh, right. Yeah, I am seeing. Right? The picture's already forming that this tree is pretty dang close to average, slightly shorter than. Right? So I'm getting -1 in the numerator, getting this in the denominator. Right? So this is, right, there's my z-score for that particular tree. Okay? Do I see an answer choice that says that? Yes, I do. Bam, right there. Okay. And then for complete context, let's look at the z table again. Right. Just look at my number, -0.17. So -0.17. All right. So this cell right here, let me zoom in where you guys can see this class. So 0.43, that means 43%. Okay. So this tree is, yeah, it's taller than 43% of trees, which implies that it's shorter than the other about 57%. Okay, pretty close to average on the short side. Okay, right, guys good? Right, and last one on this side, tree height. 320 centimeters. Oh boy, oh boy. Okay, let's do z equals. Okay, I got a 320 centimeter tree. Okay, right away it's standing out as an anomaly. I'm thinking, right, because I know my average tree is 301 centimeters in this warehouse. Okay, so the numerical value, that's 19 centimeters above average, right? With in a tree population of standard deviation of 5.79 centimeters, right? That's like this tree already at a glance I can tell it's several standard deviations above the mean, which is a really rare case. So that divided by that, okay, that's like 3.28. Yeah, more than 3 standard deviations above the mean. Yeah, which is really rare. Right? How really rare? Right. Well, let's check the z table. What does that mean? 3.28. 3.28. This cell says 0.9995. Right? That means 99.95%. Right? That means here's another way to say this. If there were 1,000 trees in this warehouse, there's only a 50-50 chance that this tree is not the tallest tree. Right? There's a good chance this tree is the tallest tree. And if he's not, then there's maybe one other tree that's taller. Right? Right? If there's like 1,000 trees in the warehouse. Right? You guys get that? All right. So that should finish page A. You guys got page A finished? Is there any question about page A? Okay. All right, let's check out page B. Right, page B. Right. And so there's the normal distribution curve again. Right? Remember mu is one symbol I'm going to use for average. I'll use that interchangeably with x bar. If you go out plus or minus the standard deviation, it tells you right there under the curve what percent that is. I think I asked you guys this back on Friday. Right? Do you guys remember? So plus or minus one standard deviation covers how much of any population? Like 68%, right? 68%, right? And then plus or minus two standard deviations is like 95%. Plus or minus three standard deviations is like 99.7%. If you take a stats class one day, but a lot of you guys will, right? That's going to be a test question. Right? It's called the 68, 95, 99.7% rule. That's what that is, right? And there's a tiny, tiny, tiny percentage that's on these tails, extremely high or extremely low, right? Right. So here's average, mean average, standard deviation, z-score. Okay, so we see all that again. Okay. Ooh, but now I got a new story. I got these bottles. Let's see, these are like water bottles. Okay. Now my bottles, at a glance, looks like are 2 liters. That may not be the case on your paper, right? Let's say, hey, what if you're working for like a consumer protection agency for the government, and you want to know, is this particular bottle manufacturer like misadvertising? Are they advertising, say, 2 liters, but they're not really filling 2 liters? All right, let's test. Right? Let's go grab a bunch of random bottles. Right? We'll measure what is the volume, and we'll see if they're actually selling what they're advertising. Right? So I pulled 6 random bottles off the shelf. Right? And you guys also have 6 random bottles? Guess that? Right? What is the mean? What is the standard deviation? Right? So let's start to crunch this data. Right? Right, so you guys got calculator? Calculator? Right, we'll just let the calculator handle like these formulas right here. Let's clear out what's already there. So hit second 0. You guys hit second 0 to reset it, and then scroll over to yes and hit yes. Right, you guys clear out the calculator? Right. Right. Now hit second stat. Right. You guys hit second stat, get 1 variable. Right. Who does not have 1 variable on their screen? Is everybody's good? Hit enter. Right. Then hit the data key, data. Right. It should say x1. Right. Guys, who does not have x1 on their screen? Everybody's got x1? Right. Everybody's good?
Stat.
Yeah, let's see. There you go. All right. All right. So also here, guys, look at this. I gave you all the volumes in liters, but the question's in milliliters. Oh yeah. Yeah. Guys, how do you go from liters to milliliters? You multiply by a what? How many millimeters are in 1 meter? 1,000. Yeah, 1,000, right? 1,000, right? So that's 3 decimal places, right? 1,000, right? Right. So okay. Swap out meters, liters, same idea. We're gonna scroll 3 decimal places for all these. So my first bottle is 1.970 liters. I'm gonna interpret that as 1,970 milliliters, and that's what I'm gonna type in the calculator. 1,970. Okay. You guys see that? Take your first bottle, multiply by 1,000, type that in. Yep. Okay. Then scroll down. Frequency 1. Yep, there's only 1 of those bottles. Right? If you're doing hundreds of bottles, might be several entries there. So scroll down again. X2. My second bottle is 1,980 milliliters. Right? Scroll down. Well, right. I got 2. I'll just say there's 1. I'll just retype it again. Okay. My third bottle. Okay. Scroll, 4th bottle. Scroll, 5th bottle. Scroll, 6th bottle. Okay. Now I've got my 6 bottles plugged in. You guys got your 6 bottles? Working on it. All right. All right. Who needs help? Who needs help? Okay. So everybody's good? Okay. All right. I'll hit statvar. Statvar. Right. Should say n is 6, as in you have 6 bottles programmed. Right. You guys got n equals 6? Everybody's got that? All right. Scroll to the right. X bar average. That's that box right there. Right. So mine is 1990 milliliters. Okay. So yeah, it looks like this bottle manufacturer, at least on my paper, is Yeah, underfilling the bottles a little bit. Maybe they're advertising 2 liters, but it's a tiny bit less, not a lot less. Okay. But there's a little bit of variability. I mean, clearly there's variability. They all have a little bit different liquid, right? Maybe back at the manufacturing plant, back at the factory, it's like they got some conveyor belt, they fill like liquid, bloop, and the next bottle, bloop, next bottle, bloop, right? And then if you stand back and look at all the bottles, maybe all the liquid levels are a tiny bit more, tiny bit less. So what's the standard deviation? So scroll to the right one more, get like a plus or minus value of, my case, I'm going to call it 15.5 milliliters. Okay. Okay. What that means is if there was like 1,000 bottles on the shelf, right? That and let's say it went through and measured every single bottle, right? Like all 1,000 bottles. Okay, the average would be 1990 milliliters. Yeah. Right. And then if I do 1990 milliliters plus or minus about 15 milliliters, that should cover 68% of bottles. And then there'd be about 1/6 of bottles that are like really underfilled, less than that. There'd be about 1/6 of bottles that are really overfilled, more than that. Okay. Hey, you guys got that? All right. All right. Now let's go grab a 7th bottle. Right. The 7th bottle has this many milliliters. So what's the z-score for that particular bottle? All right, you guys ready to do z-score? So remember, z-score was like the individual value minus the average, all compared to the standard deviation. So we're gonna do. Okay, so I'm looking at this many milliliters minus the average, which was this many milliliters on my paper, which is different on yours, probably. Okay. And then group that in parentheses and then divide by this many milliliters standard deviation. Okay. So I'm getting a z-score on this particular bottle. Okay. I'm getting this number right here. Right. Now, even though we all have different papers with different numbers, I'll tell you what, I did make everybody's values here integer values. Might be positive, it might be negative, but it should be like something 0.0. I have 2.0. You might have 1, 2, 3, or -1, -2, -3.
Mine's 0.99.
Call that 1.0. There you go. Yeah. All right. Okay. You guys get that? All right. And then last question here with these bottles, what percentage of bottles have less liquid than that bottle? And so it's like if you look back at this bell curve, how much of the curve is shaded up to that point? And since I have a z-score of 2, that's this particular bottle, I'm looking at a z-score of 2, right? And I could just add up all the parts of the curve up to that point. I really want to do this 2 different ways, and I'll get 2 slightly different answers. One way is just to play off this graphic right here. Right? So I got this tiny tail is 0.15%, plus this bit is 2.35%, plus this is 13.5%, plus this is 34, plus 34, plus 13.5. All right, so all that curve adds up to 97.5%. Okay. Okay. Now I left a little space because I also want to check the z table on the back. And this should tell me effectively about the same thing. Right? So if I have a z-score of 2 on the nose, 2.00, that is 0.977. That's like 97.7%. Right. So I'll write that to you. Okay. Is 97.7%. Okay. Right. So either of those would be acceptable. Okay. About the same thing. All right, you guys good? All right. Any questions so far? All right, you guys all right? All right. Now it's going to be about the lab part of this. So tell you guys what's going on, and then send you guys back to the lab area. Get the height, your height, and 4 friends. So you're measuring your height, your friends' heights, compare a bunch of numbers. Okay. And let's say these 5 values were representative of, let's say all students in the school somehow, right? And then you want to know, well, these questions. What's the mean height? What's the standard deviation? And then where do you kind of rank, right? Maybe you're shorter than average, maybe you're taller than average, and then like how short or how tall, right? So get a z-score for yourself or your own height, right? And then this last question is, what percentage of people are taller than you? Now, guys, notice how that's phrased. It's kind of the opposite of this question with the bottles of how many bottles are filled like less than, right? This is saying like how much is greater than, right? Guys, isn't that like finding this tail on the right, right? Like, how about this? What if you got a z-score of 2? Like you're a super tall person. Z-score of 2 is a pretty tall person, right? Right. Now you could say I'm taller than, say like let's call this 98%. Is that all right? Like 98%. I'm taller than 98% of people, which means that how many people are taller than you? Like 2%, right? And that would be the answer to this box. Right? If you have a z-score of 2, you say, well, 1 minus 98% is like 2%. Okay? You guys got that? Right. One last thing before I send you guys back there is since there's only going to be 5 values, if you want to crunch this all with your calculator, which is a good idea, go ahead and clear out your data so there's not like a 6 bottle from before hanging around. So I'm going to hit second 0 and then scroll over to yes and reset the calculator. Okay. So now it's all reset. Here, maybe just hit second stat, 1 variable, then hit data, so you can start typing in your heights. Okay. Okay, guys good? All right, so all the major sticks meeting back in the lab area. I will walk around and help you guys out, and we're doing this for the rest of class today.